yeah, I'll keep this in mind for maybe for one of the next sessions.
Yeah, then I suggest just again 2 or 3 of the last one. Like way.
I would like, if there is no specific task requested, I would like to I would like to go through a specific one, which is task number 14R. It does not look like very spectacular or something. It's this one. Can you see my screen? I have to check. Yes. So task number 14R, which is just the square root. 14R. So just the root out of the root of a to the power of 4. So yeah, why does this show up in this task set at position? A quite difficult task unless it does not look like it. So why could this be a difficult task? So if you've checked with the sample solution, I will give you the result right away. This is the result of this simplification. So does any of you know what this actually means? These two vertical dashes between.
It's a modulus.
Yes, is this the English term for it? Yeah, of course. If you say that. Okay, modulus. I'll write it down.
It refers to only magnitude.
Again?
It refers to only magnitude, like only the value.
Yes, okay, then that's correct. So the modulus operation means that you will end up with the absolute value, or yeah, sometimes called magnitude of a in this case. So of the variable between the dashes or the. So why does the modulus operation show up here? Actually, this is because we are canceling a square with its counter operation, which is the root. So whenever you are canceling a square with a root, you will have to apply these absolute value dashes or this modulus operation. But why is this? Because you have learned that if you, for instance, have the number 3, then you square it. This is going to be 9. And if you want to have the square root out of 9, this is going to be 3. Yes, that's true. Both of this is true. But there is one thing to keep in mind, because if you're now doing not the square operation at first, but you have to do the root operation at first. And that means that you don't have the base of the exponentiation as your given value. So you have to think about what could the value, the base value of the exponentiation have been before it was squared. And yes, so this leads you to the following conclusion, that it's not only possible that the original base value was positive 3, but it could also have been negative 3 to the power of 2. This would be 9 too. But if you would still go with this one, then you would end up with another result in the end that with than the term you started with. And that's why we are using this modulus operation here to cover both of the possible start values for the exponentiation, for the squaring. So this means that only you can only tell that this term is equal to the absolute value of a, because at the first thing you do, you're working from the inside to the outside. The first thing that you do with the unknown variable, with a, is that you square it. And after you squared it, whether you're squaring 3 or negative 3, you will always have 9. And then you're taking the root out of a squared as a whole new term. So you're taking the root out of 9 in both cases. And this, in both cases, will be positive 3. So the root out of a positive number will never be negative 3. And this rule still is still valid. And yeah, that's why you will, in both cases, end up with a positive number. And that's why this modulo becomes necessary in this case, because the result of this outer operation, of the root operation, can never be a negative number. And that's what you have to keep in mind. But of course, this is not still not complicated enough, because if you have a look at roots with exponents, it's the root exponent. Or is there another term for this? I would call it the root exponent. Or is it the radicand? No, it's not the radicand, but I think it's the root exponent, right? Okay. So if you have something like, for instance, okay, let's say -8. What about this? Can we solve this? Because we said that, for instance, we could never solve something like this. This does not have any result because we cannot have a square root out of a negative number among the real numbers. So there's never going to be, if I'm replacing this with a variable name like a, there will be no result within the real the real numbers greater than 0.
I think it's -2 at the square root.
In this case,
the third cubed root of -8.
So the cube root of -8 is -2. So in this case, if there is another root exponent, in this case, this would have been 2. In this case, there is a result for this term simplification. And that's exactly what you may have also spotted in the sheet with the rule, which is in our material folder, that this root rules are a lot more complicated than the exponential rules, because you can spot that there is that it is distinguished between an odd root exponent and an even root exponent. And in case there is an even root exponent, so the same goes with 2, 4, 6, 8, and so on. Or you always, if you are canceling the root with the square, you always have to apply the modulus operation. And this is a very, very important thing to keep in mind, because this means that if this would have been an equation or part of an equation you would have to solve, there might be 2 possible solutions for x, because you only get an information about the absolute value of x. This means the solution, the actual solution for x, could either be the positive value x or the negative value x. Okay. All right. Anyone who did not get what I just explained? So yeah, maybe we can do the example up here again. So what would we have to do if we would not have known that the result of this particular term is the modulus of a? So the first thing we would have done maybe is just to split up the a to the power of 4 into a squared times a squared, right? So this is what I would have done. And then you have you can apply one of the root rules. One of the root rules tells you that you can write any a times b as square root of a times square root of b, or any root. So this can be an arbitrary root exponent. Okay, so if we apply this rule here, then we can do the following. We can have root of a squared times root of a squared. Just a second. Now my OneNote is again getting slower. Yes, and if we have done this, next step could be what I just said, that we have this modulus operation coming up in here. A and A. So because you cannot determine whether this A was a negative or a positive number before it was squared and then the root was taken out of it. But you cannot tell if this is a positive or a negative number. You can only tell that this term, square root out of A squared, is equal to the absolute value of A. No. Okay. But now there's another thing. So what is the product of modulus A and modulus A?
Modulus A whole square.
Yes, okay, you could think of this as, just a second. So you could think of this as modulus A squared. Yes, that's true. And what can you tell about any number which gets squared? Any number that is getting squared. So if you have, for instance, -3 squared, this is going to be
Positive.
Positive. It's going to be +9, for instance. And it doesn't matter which number you will have as the base of your exponentiation with the exponent 2. It doesn't matter. You will always end up with a positive number. So you can also tell that this will turn out to be the root of A squared. So you don't need the absolute value dashes in here. Actually, you wouldn't have needed them anyway, because the modulus operation tells you that this is a positive number. And yeah, of course, a positive number squared is still a positive number. But yeah, anyway, you can skip, or you could just get rid of these modulus operation at this point. But now you again have the square root out of A squared, and then the rule with the even root exponent again applies, because if you cancel the A squared with the square root, then you have to apply them again. And yeah, this gives you the final result, which is the modulus of A for this task. So this is very important to keep in mind, and I think we will always, we will get to the point where some of you will miss this at another task when it's about solving equations, because this is a very common mistake among a lot of students, that they don't pay attention on applying the modulus operation when canceling any square with the root. One other another aspect where this is gonna become tricky is when you're swapping root and exponent, because it's quite usual to do something, or the nth root out of a to the power of m is the same as the nth root of a whole term to the power of m. So this looks like another rule, and maybe some of you have heard of this rule at school or somewhere else. But in this case, it is again very important, and I have searched for a long time until I found a rule set where this is also part, is that n, again, in order to apply this rule, needs to be an even number. This is very important because this rule does not apply whenever you have an odd exponent. Or yeah, of course, no, that was not actually true. But the condition is if n is even, then you can only apply the rule if your base or your radicand, that's what it's called, your radicand is greater or equal to 0. Okay, let's check what this means. So n is if n is even, x needs to be greater or equal to 0. If n is even, of course, now it's a in my example, a needs to be greater or equal to 0. Okay, so yeah, what does this mean? For example, where is this not applicable? If you think of something like the third root out of -2 to the power of 4. So some of you would think of writing this as, or just let's say -8. Some of you would think of rewriting this as the third root out of -8 and this whole thing to the power of 4. And then some of you would say that this in the middle, of course, is -2. And then you would raise it to the power of 4, and then you would turn out with +16. Okay, I think I made a little mistake because this is just a second. I have to think about this. But actually, this first transformation is not true if you apply the rule above. And now you can you can watch me guessing if this is actually true, because if we would do the operation in the right order, we would have to go from the inside to the outside, and then we would at first have to apply -8.
But now your n is odd, so the rule does apply.
Oh right, I'm sorry.
Cubic root.
I confused myself with my own example. Okay, yes, of course you have to. Yeah, you have to have an even n, for instance, with square root. Ah, damn it. Okay, if you have the square root at this place, yeah, of course. Now I have to think about another number. So like this, yes, now it will work. So if we do this and swap the, or just pull the exponent to the top, we would end up with the square root out of -4. And then some of you would just say, oh, there is no solution for a square root out of a negative number. And so there's no solution for this. Right? So this would be a proper way to prove that there is no solution for this term, that this term is not a real number. Is everyone agreeing with the fact that this is not a real number? Sorry? You were agreeing. So you would say this is not a real number. Well, I say this is a real number because I've done something wrong. I applied the rule, even though I can't apply the rule actually because n is an even number and my a, which is -4, is not greater than 0. So there is a mistake in applying this rule above in this case, because I have to pay attention on the right order in which I have to do the simplification of such a term. The order always goes from the inside to the outside, and that's why I have to start by calculating -4 to the power of 4. And if I do so, I will have -4 times -4 4 times. And if we multiply, this is going to be a positive number, 16. And in this case, of course, this will be 16 too. And now we have 16 times 16. And this is 256. Of course, positive number and positive number multiplied is a positive number again. And then we have the square root out of 256. And now everybody can think of the result for this, but yeah, actually I will just leave it with the square root of 256. But I think we can all agree on that this indeed is a real number, right? So as you can see, you have to be very careful, and I also confused myself a minute ago. So always be careful if you have an even root exponent, that you have to pay attention on the right order in which you simplify your term. So you cannot apply this rule, for instance, at least. So this one and this one with the modulus operation, these are the most dangerous things when working with roots. So these two aspects always lead to mistakes in exams and always lead to mistakes in tasks which are quite similar to these ones. So just a second. So you think of something like this. Yeah, okay. So this. Okay, in this case, this is, yeah, okay, this is quite simple, actually, because you would say that this is not a real number, and you would be all right. So this is no real number. You can spot this right away. But maybe if you want to violently apply the rule above, you could say that you have -4 to the in here, and this is the root exponent 2, and you want to apply the rule up there. Then this again applies because you have an even root exponent, and your a, which is now, of course, it's raised to the power of 1, but you could still think of it being raised to a power. But your a is still, the base of the exponentiation is still negative, and that's why you can't apply the rule. So you could not rewrite this term as, for instance, so this would be wrong if you would rewrite it as the root out of, yeah, okay, but this wouldn't change anything anyway. So if you would swap the exponentiation 1 to the top, this wouldn't change anything because you would still be left with the square root of -4. But yeah, this was a better example for it because, yes, in this case, you would have come to a false conclusion if you would have applied the rule, because you would have come to the conclusion that there is no real solution, or that this term is not a real number, but actually it is. And we could prove this by just applying the right order for the simplification process. Okay, anything unclear about this, or any question about, yeah, these two traps? All right, well, there's some kind of plane outside of my window. I hope you can't hear it. Okay, you wanted me to go through some of the tasks from number 14, right? So is there another task, another special task or certain task you want me to calculate?
Can you do the number E from task 14?
Okay, 14E.
No, sorry, 15. Sorry, 15.
15E. Were you the one who wrote this into the forum?
Yes.
Yes, yeah, I will definitely do that because I highly appreciate it that you put it into the forum. So we'll do it if there is no further request for a task out of topic number 14.
And now can we just do one of the last ones of 14, like X or Y?
Okay, yeah, let's do task number X. It doesn't look that horrible that like task number Y. Yes? You mean this one? Yes. So in this case, you don't have an even root exponent. That's always something to distinguish. So if the root exponent is uneven, is odd, then you may have a negative radicand below the root. Because in this case, there is a solution for the counter operation. So you can have you can have a number, a negative number raised, which is equal to -2 if you raise it to the power of 3, because a negative number times a negative number times a negative number will still be will again turn out to be a negative number, and that's why there may be a solution, or there is always a solution for a root with an odd root exponent and a negative radicand. All right, so you wanted me to calculate task 14x. 14x. Let's do it. Just a second. I have to check if I've got a sample solution for this. Okay. Task number 14. 14x. 14x. 1 over a to the power of 3. A squared minus 4b squared cube root a to the power of 9 minus b times 16 a squared b squared. Okay, maybe this is yes, a good chance to give you some kind of or to draw I'm missing words again to get your attention on another very important topic, which is the order of operations in general. Because, for instance, in this case, I could imagine that there might be some of you who have problems to figure out the right order be done. And there's quite a very helpful mnemonic, or yes, mnemonic is in German, it's Eselsbrücke. I don't know if there's another term for this in English than just mnemonic. So just a short, an abbreviated sentence in which you can use to remember the right order for operations. And there is a sentence like this: please excuse my dear Aunt Sally. So what does this stand for? So every capital letter at the beginning of each word marks a certain operator or operation, which needs to be done in this exact order if you're simplifying a term. So the P stands for parenthesis. So this means, parenthesis like these. These always need to be treated as the last one, or yes, as the first one. So whenever there are parentheses, you have to deal with them as the first. So for instance, usually there is a times b plus c. And in this case, you would have to do this operation at first. But if there were parentheses around b plus c, they would have the higher priority, and you would have to deal with the b plus c at first, which is inside the parentheses. Okay, the E then stands for exponents or exponentiations. Yes, exponentiations or exponents. So if there is some a to the power of b, this is always going to be first to deal with. Afterwards, it's multiplication and division, which is the d. And then as the last, there is addition and subtraction. Of course, together with exponents, there's also roots at this position. Because this is another very important rule we should note down on our note sheet here, which I will again upload after our today's session. So if you have any root with root exponent n and a to the power of m, this could not only be written in this way. So actually, this is an extension of this rule we already set up here. But this can also be written as, or maybe I'll just put it in the box up there. Just a second. No, it's not a new rule actually. So we put it in. No, come on. No. It's getting slower and slower again. So this could be also written as, does anybody know? Anyone? So if you want to rewrite this root term as an exponentiation term, you can do so by writing a to the power of a fraction, which is m divided by n. So this would be the exponent you would have to use in order to rewrite a root term. So if you have a root term like nth root out of a to the power of m, you can rewrite it as a to the power of m divided by n. But this, of course, still applies in this case. So always pay attention that n is an even number, that if n is an even number, a needs to be greater or equal to 0. All right, so let's use these rules and this helpful little sentence in order to solve our task 14x. Does anybody have an idea how to approach this task 14x? Yes, that would be an idea. So if we could just deal with only exponentiations or only roots, we would have to transform every root into an exponentiation, for example. That's a good idea. So how can we do this? So the first fraction will then be 1 divided by a to the power of 3/2 times, so this will remain a squared minus 4b squared. And what happens in the denominator? Yes, so 8 to the power of 3. Oh, let me write it down in this way first, and then we can simplify. Minus b times Yes, okay, so we have to rewrite this first as 4ab whole squared, right? And then we can apply the rule we applied for the other part terms. So this is a squared minus 4b squared. And down here, now we can write 9 divided by 3, of course, it's just 3. And now we can apply the rule again. And in this case, this will be 4ab to the power of 2 by 2, or 2 divided by 2. And yes, as you can see, this is canceling. But, oh, now I nearly made the mistake I should not make, because at this position or at this point, you can see that you have to that you are canceling a square with a square root. And we had this before. So actually, we would have to write b times the modulus of 4ab. You see that? So actually, we would have to do this. Just let me think about it. Yes, should be necessary to do it. Yes. Okay. How can we go on? Sorry again, please. Could you repeat? Okay, so at first we could write all this on one big fraction, right? So up here we have just 1 times, 1 times this term. Would you want to multiply this here, these terms? Yeah, actually, I was wondering if we could. Damn it! I made a. Just a second. I have to think about one thing for a second before I proceed. That's the problem. If I don't solve the tasks before I have to let you see me guessing or see me thinking. I actually don't want to do this. I have to think about if these modulus operation really has to apply at this position. Because actually we started with this term, which was 16 times a squared times b squared, and 16 of course is positive, this is positive, and this is positive. So actually there's no reason why there should be a negative number in the radicand, and that's why I think we can skip the modulus operation at this point. But I'm not sure about it at this time. Actually, it's a thing about term simplification and solving equations. Okay, let's proceed. Maybe it will modify itself. So yes, you can do this, but of course you don't know if it is A, which is negative, or if it's B, what is negative, and if it's so it could be that A is positive and B is positive. It could be that A is positive and B is negative, and A negative and B positive. So you would end up with 4 different cases, and that's quite complicated to deal with. Yeah. But I think that in this case, there should be actually there can't be an exception for this. Okay, let's look where it leads us. So what about the denominator? What can we do about the denominator? So you want to do a 3/2 times a to the power. So of course here there are parentheses too around this expression. So you have to multiply a to the power of 3/2 times a to the power of 3 and subtract a to the power of 3/2 times b times 4ab. Okay. You can, yes, that's what we can do. A squared minus 4b squared. And now we can apply one of the exponentiation rules, because this is going to be 3 plus 3/2 in the exponent, if you remember this rule. And 3 plus 3/2 is 9/2. Should be correct, right? Yes. Yeah. What can we do with the other term right here? I think there is no need for this modulus operation. I will think about this and I will tell you tomorrow if they have to apply here or not. But I think we can get rid of them, because the original term at this position was definitely a positive term. And that's why you can skip the modulus operation at this point, or you can get rid of the dashes. Yeah, but I'm very sorry about this. I can tell you right now, I'm confused myself a little bit, but yeah, in order to proceed with the solution, I will leave it like this, because obviously this term is positive term, and consequently the root will also be a positive value. Yes, let's proceed. Yeah, but actually the same would apply here. So actually this would have to be just a and not the modulus of a. But yes, I will look that up and I'll tell you tomorrow. Okay, so what can we do about this term in the denominator? Yes. And 3/2 plus 1 makes 5/2. Of course, there is still 4, and there's b times b, which is b squared, correct? And what can we do now? Okay, so you would kind of rewrite it again as a root term, because now it would be easier to see any similarity. So if you would rewrite this as like this, is that easier for you? Well, I think I would not do this at this position, because it's actually a good idea to just use exponentiations in your term. It's nearly always easier. But I thought of some kind of factorization, because obviously this and this is already quite similar. So there's negative 4b in the numerator and negative 4b in the denominator. And maybe there's some way to cancel them when we rewrite this expression. So let's have a look at this. Sorry? Mm-hmm. Yes. Again, how would you cancel them? Mm-hmm. I don't know. Maybe there's another way to. Yes, that's what I'm currently thinking about, is looking at these two terms, is to pull a factor out of both this one and this one. So what could be a common factor of these two summons? Actually, I thought of, yeah, considering, just a second. Okay, could you just tell me what to write down and I'll do. Mm-hmm. Sorry, again, I didn't understand. A?
Power to the 5. Simon.
Yes, one at a time would be great.
A power to 5 divided by 2 multiplied by parentheses a squared minus 4b squared.
So let's check if this is true by doing the counter operation. So if you get rid of the parentheses again, you would have a to the power of 5 halves times a squared, and this minus a to the power of 5 halves times 4b squared. And now you have a, and this will be 2 plus 5 halves. And 2 is 4 halves plus 5 halves is 9 halves. So this looks very, very good. And this, of course, is, yeah, this is still already what we were hoping for. Yes, that was very, very good. So we can pull out a factor of a to the power of 5 halves out of this two summons in the denominator. Okay, can everybody see this? It's a little difficult to see that, yeah, there's actually, so what I would have done is just to extract, to pull this one apart into a squared, and then I would have looked what is left of it if I pull a square out of there, and then I would have come to the conclusion that it is 5 halves too. And yeah, that would have been my approach. But yeah, if you see that there is a common factor of a to the power of 5 halves, this is a very, very good thing to see. And yeah, and that's also a thing which is highly simplifying our term, because now I hope everybody recognizes that it is possible to cancel the numerator with one of the factors in the denominator. And this will leave us just with the term 1 divided by a to the power of 5 halves. Or you could write this as a to the power of negative 5 halves. Okay. Okay, I think this is the sample solution, but actually it was another solution approach than I did myself 1 year ago, because I looked it up. I still have my notes from then. But this was another solution approach, but with the same outcome. So yes, this is the correct answer. As I said, I will look up again the thing with the absolute value with the modulus operation. But in case we skip the modulus operation, we end up with the correct answer in this case. But of course, there are maybe 100 or 1,000 other approaches for this task. But what is the important thing is that your final result should always be a to the power of negative 5 halves. And yes, I hope you could at least follow this solution approach. Is there any question about this? So if there is no question, feel free to give me a green reaction or thumb up. All right.
Simon, can I say something?
Yes, please.
This approach looks very difficult and big. I mean, we could do it in an easier way, right?
Do you have an easier approach for the task?
Yeah, I just did it in like 2 lines.
Oh, then just hit me just a second. I'll make some space for your solution. This will not work. Yes, it works. Okay. Yes, let's go for it. So this is the original. Yes, please. Or do you have it in a digital written way so you can share your screen and just show us?
I actually don't. I actually wrote it on my paper, so
Okay,
I just got rid of the roots first.
Okay,
and
so
I didn't. Yes, I
did
just
the
got
same step like this one?
yes, just like that. Then I took a from that. I guess if you get rid of the roots, then you're left with on the denominator is a to the power cube minus b for ab, I guess. So you're left with b for ab. Then that's basically for ab square. Then you just take a common from the denominator. Then you're left with a square minus 4ab. Then you cancel out a square. And
okay.
then you just
okay, I understand what you did. Let's do this a little slowly just for a second. Okay, so this will look like this, and there will be a 3 halves times a to the power of 3 minus, yes, oh my god, this is so much better and so much easier. So, but yeah, okay, we were dealing with this modulus operation then, and that's why we couldn't multiply these two b's or pull out the a of this modulus operation. But if we could get rid of the modulus operation, then of course this is a simpler way to approach the solution, because now we have an a in here and we have an a in here, and this is a common factor, and this common factor can be pulled out of the parentheses, like there will be a 3 halves times a times, and then is 1a less in here and 1a less here. And then we are already at the point where these two will cancel, and yes, beautiful. No.
Nice job.
Like this, and now we are already there because we have a 3 halves times a, and of course this is a to the power of 5 halves which is our correct answer. Very, very good. Thank you. All right. Any other notes on this topic? Otherwise, we would jump right into topic number 15. So if there is no question, let's proceed. With 15. There was a special request for task number 15E, if I remember that correctly. So task 15E. I went over this task earlier today, and yes, so maybe there still is another one of you who wants to do this for everybody. But yes, let's write down the task. So this task was about rationalizing the denominator of a fraction, and the certain task was this one. Okay. Any idea how you could deal with this?
Multiply by square root of 5 minus square root of 3 over square root of 5 minus square root of 3.
Minus?
Square root of 3.
So you want to, yeah, some kind of extend the fraction. Yes, I don't know does anyone know what is the correct term for doing this to a fraction? So in German it's erweitern. I don't know if there's an English term for erweitern. So you would just multiply a certain factor or another fraction to your original fraction, and this one is just 1. And if you your original number or your original term, it will not do anything about its value. So this is going to be the same as before. That's why it's equal. So this will stay the same, but you will add or just multiply this fraction to your original fraction. Is it expanding a fraction? I don't know. But yes, what does this do to your term?
Then he can go with the a square minus b square rule.
Yes, correct. So we can apply the third binomial formula in the denominator. So if you have a look at the denominator, at these two, this looks again quite similar to our a plus b times a minus b. So we added this fraction term for a special purpose because we wanted the denominator to look like this. And yeah, that's why we added, or we put this term as a factor in the front. And if we apply this rule, we will end up with the following in the denominator. So the rule is a squared minus b squared. And what does it mean in our example?
5 square minus 3 square.
Is that true?
Yes.
Actually,
the answer will be,
it would be
yes.
square root of 5 and square root of 3 squared. Correct?
Yes.
Because your a and b are the square roots of 5 and 3. And that's why, what is the correct answer? What is the denominator?
Just only 2.
Sorry?
Or 5 minus 3.
5 minus 3, correct. Because, yeah, I will leave it like this. 5 square root of 5 minus square root of 3, and both of them squared on their own. Come on. Why did that? I just want it to disappear, and it does not disappear. What? I just cannot recommend OneNote to anybody. So like this, and of course, this is another thing. So we used to have And now we have a term like this one. And this is actually a difference because now we are at first doing the root operation and then we are doing the squaring. And yes, it's like with other operations that where you can't switch the order, you may not switch the order of these two operations unless there is a positive radicand. So this is again the rule we were dealing with up here, so that the radicand needs to be positive or greater or equal to 0 in order to swap the order of these two operations. So in this case, it wouldn't matter, but yes, this is something you always have to pay attention on, the right order to whether there is the root first or the square first in case of negative numbers. All right, in this case, this will be 5 minus 3. And of course, this will be just 2. What is this? Why is there? Oh, that's why is this happening? Oh my God, I hope I will make it to the end of the meeting with this software. Okay, what about the numerator? The numerator is like this. Please don't forget about the parentheses up here when you're putting it into one fraction. Always think of using parentheses. This is very important. And now we can do the expansion of these. I also don't have my colors anymore. Where are my colors? Now, there they are. So we can do the multiplication like this, plus this, plus this, plus this. I hope everybody is familiar with that. So what would that lead us to in the numerator? Yes. Yes, okay, that's the next one, right? Root 5, root 3. Yes, correct. Yes, so you spotted that this is the same as here, so x times root 5 root 3 minus, or was it minus? Was it plus? Minus. Minus 1 5 3, and you could just think of substituting these with the letter A, for instance, and then you have 2A minus 1A, and this always turned out to be just 1A, and that's why we can. Oh yes, minus, correct, minus 2A minus 1A, and this would turn out to be minus negative 3A, and that's why we can write 2 times 5, of course, is 10 minus 3 square root of 5 square root of 3 plus 3. Yeah, of course we could have connect these two. So 10 plus 3, of course, is 13. And in the denominator, this is going to be 5 minus 3, which is 2. And then, yeah, we could do
Simplify.
yes. How could we simplify it?
13 divided by 2.
Yes, you could split up the fraction or the sum in the numerator into 13 divided by 2 minus
3 over 2 times 15 square.
Yeah, could do as well. You could do, yeah, no. 5√3. And can we do something about this?
Yeah. Multiply. So it's going to be 15
Yes,
square.
so there's one of the root rules which helps us at this point. So this is going to be 13/2 minus 3/2 times the root of 5 times 3. And 5 times 3, of course, is 15. Yes. No, OneNote is the thing I want to use in this course. Okay. 13/2 minus 3/2 times square root out of 15. I think that's as easy as it will get. And that's also what the sample solution tells us as the correct result. Okay, is that clear to everybody? So this is the very, very extensive way to write it down, of course. Can see a thumb up reaction. Is there, yes, thank you. Is there any other request for any other task from the task sheet?
Maybe also D from 15.
Yes, 15D, all right. Let me have a look, or can someone just, well, I will look it up just a second. 15D, there we go. So is it just, is it this one, 28 divided by 4 plus square root of 2?
Yes, this one.
Okay, so how are we gonna deal with this? Any idea?
Would we multiply it by like 4 minus 2 squared? Yeah, divided by 4 minus, yeah, the same way that we did like
Yes,
in the previous way.
correct.
Okay.
Actually, it's exactly the same approach like in the task before. So if we just expand, erweitern. If we do the Erweiterung of the fraction, it would look like this. And yes, no, damn it. And then we can do the same we did in the task before. We can have a look at the denominator, and then we can spot the third binomial formula in there. And then this is going to turn out to be 4 squared, which is 16, minus root of 2 squared. And our numerator is 4 minus 2 minus root of 2. Please don't forget about the brackets, the parentheses. And yeah, turns out that this was task D, and there is a reason that this was task D, because as you can see, it's a little easier than task E, because now we can expand the parentheses in the numerator, like 28 times 4, which is 112, correct? Yes. Minus 28 times square root out of 2. And in the denominator, we'll go with 16 minus, yes, and root and square cancels each other, and we are left with 2. And at the end, we can, yeah, of course, 16 minus 2 is 14. And then, yeah, some of you may already have figured out that you can divide 112 by 14. Should be possible. Just a second. Yes, 8 times 14 is 80 plus 32. So this is 112. Yes, I actually did this a second ago. Yeah. Okay. Yeah. So 112 is divisible by 14, and this is 8. And 28, of course, is divisible by 14 too, and is 2. And that's why this is the final result of this task. Of course, it would also be true if you would pull the factor 2 out of these two summands. As you've learned how to factorize a term, this would also be true if you write down 2 times 4 minus square root out of 2. So both of these results would be correct. Okay. Any other question? Could everyone follow this derivation of the result? Right, looks good. Yes, just a second. I received another email from Mrs. Reinking because I asked her if she would like to join our tomorrow's meeting in order to let you ask some questions. Just let me have a look. Okay, she does. She texted me that she would be available for 5 p.m. tomorrow. So yes, that's actually pretty good because then we can walk through another topic before 5 p.m. A very short topic, and yes, then we will have Mrs. Reinking with us at 5 p.m. tomorrow, and she's going to answer your questions about studying in Germany and at the HAW. And afterwards, we will go on with tomorrow's topic, which is going to be logarithms. So yes, the task sheet for tomorrow should be accessible to everyone right now, as well as the material folder. And yeah, I hope that you will have the time to approach at least some of the logarithm tasks. They are not that extensive, so well, of course, there are 2 more tasks I just spotted. Oh, okay. So there are some more tasks about logarithms, but as I already told you, for the first day, it's okay if you do just, let's say half of the tasks of every topic, because the principle will always stay the same. So maybe you can always just solve the first one of the tasks in the middle, and maybe the last one, because it's going to be the most difficult. But yes, so the task sheet is uploaded, the materials are accessible, and I hope you will be able to do some of the tasks. Okay, any question concerning today's topic, exponentiations and roots? Or are you satisfied?
I guess that's more than enough.
You're completely satisfied.
Yes, I know it's very, very exhausting to do mathematics for nearly 3 hours. But yes, I can tell you that it's exhausting for me too. And that's why, we will make an end right now. And I hope you will see each other tomorrow again, completely relaxed and ready for another 3 hours.
Then good evening.
Okay.
Yes.
See you tomorrow.
Goodbye, Simon.
Bye.
Thank
See you
you.
tomorrow.
See you tomorrow. Bye bye.
Thank
Bye.
you.
For your efforts. See you tomorrow. Tschüss.
Tschüss.